All right, so welcome to tonight's session. I'm basically combining 4.1 and 4.2 together into one session on rational functions and asymptotes. Everything I do today in this session is going to be useful when you work on the assignment. So definitely watch this before you do the assignment, and you should be good to go. All right, just get everything set up so I can write flat. It's always much more comfortable than if I try to write with my stylus up. All right, so 4.1 and 4.2, what do they cover? So 4.1 covers finding domains of rational functions, finding vertical and horizontal asymptotes of graphs and rational functions. And those are the those two pieces are the things that you're doing most on the assignment. It also covers using rational functions to model and solve real-life problems. 4.2 covers mostly the graphs, sketching a graph of rational functions. I think that's supposed to be S there, graphs of rational functions. Sketch graphs of rational functions that have slant asymptotes. So the slant asymptotes is covered on the assignment. And use graphs of rational functions to model and solve real-life problems. So let's start with what a rational function is. So you should be familiar with the word rational. Rational expressions are fractions with variables. Rational numbers are numbers that can be written as fractions. So a rational function is a function that has fractions with variables in the numerator and the denominator. More specifically, they must have a variable in the denominator to be considered rational. Now, what's special about rational functions is that when you have a fraction, the denominator can't be 0. So d of x would just state I cannot talk today, which stands for denominator that cannot equal 0, because if you have 0 in the bottom of your fraction, you are dividing by 0, which is undefined. So what that means is any value of x that causes us to divide by 0 then results in what is called an asymptote, because you can't actually have that on the graph. So I've got two types of rational functions here. The first one is called the reciprocal function, and we did see that when we were learning about the different parent functions. The second one here is 1 over x squared, which is very similar, but instead of x, it's x squared. And you can see that there are two basic shapes to these. An x cubed is going to look like the reciprocal x to the fourth is going to look like the one on the right. So it's sort of like polynomials where there's two different shapes. It's the same with rational functions. There are two basic shapes, but there's a lot of variation in the middle. Like with polynomials, you could have wiggles in the middle. With rational functions, you can have variation in the middle. So you can see on both of these graphs that they appear to be, there's a graph and it starts to approach a straight line, either horizontal and vertical, and those are what are called the asymptotes. And so I'm going to just use a little highlighter here. So on the reciprocal function, I don't know if the yellow is really showing up, but there is a vertical asymptote at x equals 0, because if x equals 0, we're dividing by 0. And you can see that the graph starts to look straight as we heads towards x of 0. There is also a horizontal asymptote at y equals 0. You can see that as y gets closer to 0, your graph starts to look horizontal, hence a horizontal asymptote. Now, with the x squared function, we have a vertical asymptote at x equals 0, and we also have a horizontal asymptote at y equals 0. But the shape itself looks different. So what it means to have a horizontal asymptote here is y equals 0 means you can never get a y value of 0. Because if I try to say, let's say with a reciprocal function, if y is 0, that's f of x. So I'd be solving 0 equals 1 over x. Well, in order to solve that, I have to multiply both sides by x, and 0 times x is 0, so we get 0 equals 1, which is impossible. So that means that y will never equal x, or y will never equal 0, because when it does, you get a false statement. So that's what it means to be a horizontal asymptote, and then the vertical asymptote comes from the x value. Whew. I'm all over the place today. So let's look at the actual definition of an asymptote, because there's some notation here. And this notation you'll see again when you get to pre-calculus and we start talking about limits, and then you'll see it again when we get to calculus where you talk about limits. So the line x equals a is a vertical asymptote. So vertical asymptotes are vertical lines, and vertical lines have an equation x equals. And it's a vertical asymptote when your y value, that's the f of x, so think of the f of x as y, when your y value goes towards infinity or negative infinity as your x value approaches that special number. So going back here, we have a vertical asymptote on the reciprocal at 0. So as your x value gets close to 0, your y value is heading up or down towards infinity. Now for a horizontal asymptote, the y equals b, so horizontal lines are y equals lines. Y equals b is a horizontal asymptote of the graph when the y value heads towards b as x goes to infinity or negative infinity. So you're sort of flip-flopping. Oops, wrong direction. So going back to 1 over x, as my x value gets to the right or the left on the graph, heading towards infinity or negative infinity, my y value is reaching 0, which means that the horizontal asymptote is y equals 0. So that's just the specific definition and the notation that we use. That arrow means approaches. So approaches. So your x approaches 2 or something like that. That's just what that symbol means. So finding vertical asymptotes is actually quite simple. All you have to do is set the denominator equal to 0 and solve for x. That's all you do. And the vertical asymptote is always where the denominator is undefined, and that's where the denominator is equal to 0. So to find the asymptote, you just simply set it as 0, solve. So if you know how to solve for x, if we have quadratic x and we have it equal to 0, you know how to solve those by factoring in the quadratic formula. So finding vertical asymptote, quite simple. Now, to find a horizontal asymptote, or what's called an oblique asymptote. Now, the oblique asymptote is another name for a slant asymptote. Both the words are correct. It depends on which textbook you use on which word is used, and so that's why I'm showing both of them. So, a horizontal asymptote or oblique, a slant asymptote, that's going to look like a line like mx plus b form. That's a slanted line, while horizontal is just y equals b. So one has a slope of 0, one has a slope. That's the difference between those two. There are 3 different cases, and so it depends on your situation. And it depends on the degree of the polynomials in the numerator and denominator. So if the degree of the numerator, the top, is less than the degree of the denominator, so the top is less than the bottom, then your horizontal asymptote is always y equals 0, every time. You don't have to do any thinking, just memorize that. The degree of the top is less than the bottom, it's always 0, y equals 0. If the degree of the numerator, that's the top of the fraction, is equal to the degree of the denominator, which is the bottom, then you have to look at the leading coefficients. So let's say our function is a x to the n plus dot 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 over b x to the n plus dot dot dot. So a and b are those leading coefficients. Then your horizontal asymptote is y equals a over b. So ignore everything else. You just look at those leading terms. They have the same degree, so they cancel, like x squared over x squared. They cancel out, and all you are left with are the coefficients. So again, you don't even really have to do any thinking. The coefficients tell you the asymptote. So 2 cases No thinking is really involved. You just have to memorize the form and what to do. Third case here, if the degree of the numerator, the top, is greater than the degree of the denominator, which is the bottom, well, that's where you get a slant asymptote or an oblique asymptote. And to get it, to figure out what it is, you need to do long division, or depending on the situation, you can do synthetic division. So that's why we had to learn long division of polynomials, because you need to know how to do it in order to find slant asymptotes or oblique asymptotes. So I'm going to go through, I think I have 2 examples of each one of these. I think I have 2 for number 1, 2 for number 2, 2 for number 3, and then a 7th, an example of something which is called a whole. So you'll get examples of all of these, and I'm going to go through everything that you need to do on the assignment. Finding the asymptotes, finding the intercepts, finding the domain. I think those are the 3 things that you need to do on the assignment. That's all you need to do: asymptotes, domain, intercepts. So I'm going to do all of those on all of these examples. Okay, so example 1, and for all of these I provided the graph so you can see visually what we're finding. But on the assignment you don't have the graph. You're welcome to graph it if it helps you. So this first example, I have f of x equals -2 over x. So let's start with the domain. So the domain is all the x values that you can actually graph. Now I said that when you divide by 0, you get undefined. So any x where you have to divide by 0, any x that makes the denominator 0 is not in the domain. So your domain would be all reals except, and then you have to figure out what number is not in the domain. So it's all reals except some number. Sometimes there's 2 numbers that are not allowed. And so that comes from the denominator. So I'm going to just leave that blank, and let's take a look at the vertical asymptote. So the vertical asymptote, that is where your denominator is equal to 0. So your denominator d of x is equal to 0. In this equation we have x is our denominator. So x is equal to 0. That means our vertical asymptote is x equals 0. So you can see on the graph that when you get to x equals 0, it starts to approach a vertical line, and that's why it's called the vertical asymptote. Once you find the vertical asymptote, that's the part that's not in the domain. So for our domain, it's all reals except x equals 0, because putting 0 in for x will cause you to get undefined, and you cannot graph undefined. So now we found the domain and the vertical asymptote, and now let's find the horizontal asymptote. So the horizontal asymptote. And so we have to look at the degree of the top and the degree of the bottom. So the degree of the top, or the numerator, compared to the degree of the bottom. So if there is no x at all, if you have just a number in the numerator of the fraction, that is degree 0. So our degree of the top is 0. In the denominator, we have an x, which has no exponent. If you have just a single x, that's degree 1. So our degree of the top is less than the degree of the bottom. Every time that happens, your horizontal asymptote is y equals 0. So that is our horizontal asymptote. And you can see that on the graph, that when you draw a line at y equals 0, and we usually do our asymptotes as dashed, then our graph, the actual graphed portion, starts looking horizontal. So now we found the domain, the vertical asymptote, and the horizontal asymptote. So the next would be to look for intercepts. That is where you cross the x-axis or the y-axis. If your vertical asymptote is at x equals 0, you can't have x equals 0, so that also tells us, because if x equals 0 is a y-intercept, so x equals 0 means there is no y-intercept. Because in order to find the y-intercept, you set x equal to 0, but x cannot be 0. So we have no y-intercept. To find the horizontal, or to find the x-intercept, which is when y is equal to 0, you set y equal to 0. Well, because of our graph, y equals 0 is an asymptote, and y cannot equal 0 for the same reason that I showed several slides back. If y is equal to 0 here, and you try to solve for x, you get a false statement. So that means there is no x-intercept. Oh, I'm getting everything backwards here. So there is no x-intercept because y cannot equal to 0. So we have no intercepts for this basic graph. It's not going to cross either axis. Okay, so now I'm going to do this again. Same sort of thing, second example. Hopefully this will start illuminating things. So first off, domain. And I'm going to try to put this higher up so I have more space. So the domain is always all reals except something. And to figure out that something, you need to find the vertical asymptote. So the vertical asymptote is where your denominator is equal to 0. So our denominator is x squared. So x squared equals 0. And now we need to solve for x. And that means you're taking the square root of both sides. So I'm going to just do that in a slightly different color here. So I'm taking the square root of both sides. So the square root of x, or the square root of x squared is x. And then the square root of 0 is still 0. So our vertical asymptote is still at 0, which means that our domain is all reals except x equals 0. And so you can see on the graph that that's a really bad straight line, but if x is equal to 0, you can see that the graph head starts getting vertical when it gets close to that line. Next is the horizontal asymptote. Elsie, yes, I cannot hear you. I am assuming you can hear me because otherwise you would have said something. So, yes, sounds like you are hearing me okay. I just wanted to, I think I figured out all the sound issues that I was having yesterday. And I know that you and Hector both came in a little late, and so I'm hoping as I start going through some of these examples that will start making a little more sense to you guys, because I didn't want to have to like backtrack. So just follow along with me and see if this is making sense. So horizontal asymptote, we look at the degree of the top versus the degree of the bottom. So the degree of the top versus the degree of the bottom. So on top we have 3x plus 5. That is degree 1 because it's linear. So the degree of the top is 1. In the denominator, we have x squared. A quadratic is degree 2. So the degree of the top is smaller than the degree on the bottom, and that is our case 1. Just like on the previous slide. The top was smaller than the bottom. So if the degree of the numerator is less than the degree of the bottom, or the degree of the denominator, your asymptote, your horizontal asymptote is always y equals 0. So our horizontal asymptote is y equals 0. And you can see that if I draw a line at y equals 0, you can see that our graph starts to look horizontal as you sort of go towards the edges. So now we have found the domain, we have found the vertical asymptote, and we have found the horizontal asymptote. Next, intercepts. Now this case, we do have some intercepts, but you can see on the graph, even though it's really small, you can see on the graph that it does cross the x-axis a little bit when you're in the negatives. You can see it goes down below and then it starts going up. So we are going to have intercepts. So we're going to find both the x and the y-intercept. So the x-intercept, that is where y is equal to 0 and y is f of x. So maybe I should just write f of x equals 0. So I put 0 for f of x, and I have 3x plus 5 over x squared. So if I multiply both sides by x squared in order to get rid of that denominator, so I'm going to multiply both sides by x squared, 0 times x squared is still 0. Anything times 0 is 0. So I still have 0 on the left, and I get 3x plus 5 on the right. So the x-intercept comes from the numerator, the top of the fraction. In order to find the x-intercept, you ignore the denominator. So if the numerator is n of x, that you set that equal to 0 and you solve for x. So if I solve this for x, I'm going to subtract 5 from both sides, or I can subtract 3x. Let's just subtract 3x. So that my x is on the left. So I have negative 3x equals 5. And then you divide both sides by negative 3, and you get x equals negative 5/3. So that is the x-intercept, and you can see that's roughly there on the graph. Now, as I mentioned before, if your vertical asymptote is at 0, so vertical asymptote x equals 0 means there's no y-intercept every time. So just flat out, okay, if our horizontal or vertical asymptote is at x equals 0, there will never be a y-intercept. So any case that looks sort of like ours, where that center part is centered at the origin, most of the time there's no y-intercept. So are there any questions on either of the two examples I've done so far? Okay. And we just had someone else join late, which is totally fine. That's why these are recorded. Why does y equal 0? For the x-intercept or for the horizontal asymptote? For the horizontal asymptote. That is because the degree of the top is smaller than the degree of the bottom. So anytime that happens, so if your degree of the numerator is less than the degree of the denominator, it is always y equals 0. Every time. So if you have more x's on the bottom than you have on the top, it's always going to be y equals 0. So we had a linear on top, which is degree 1, quadratic on top, which is degree 2. So since the top was less than the bottom, that's why it's y equals 0. Are there other questions? Okay, so now I have a different type of function here. Here's my example 3. These are the ones where we're moving into case 2. So we're going to do the same thing. We're going to start with doing the domain. Oops, I'm in the highlighter. So I'm going to just put in my placeholder, domain, all reals, except blank. And to figure out what I'm accepting, what's being left out, that's on the vertical asymptote. So the top, we're going to just label these. At the top is the numerator for n, d is the denominator for d of x. So the vertical asymptote, as you said, d of x equal to 0. So our denominator is x minus 5. So we have x minus 5 equals 0. So then I solve for x, and I get x equals 5. So my vertical asymptote is now at x equals 5. And that's this point on the graph. So you can see instead of being centered with the y-axis, it's now shifted to the right because now our asymptote is at x equals 5. And so if you had a vertical line at x equals 5, that's where your graph itself starts to look vertical. So that means our domain is all reals except x equals 5. Next, we want to do the horizontal asymptote. And looking at the graph, you can see that it's not going to be at 0 because where it starts to look horizontal is above the x-axis. So our vertical asymptote, you need to look at the degree. So the degree of n of x, that's a linear, so that is 1. And the degree of the denominator is also linear, which is degree 1. So these are equal to each other. If, oops, I wrote vertical instead of horizontal. Horizontal asymptote. So if your degree of the top is the same as the degree of the bottom, that is what we call case 2. So I'm going to go back to our slide where we had the different cases. So this is case 2. And so I'm going to, so instead of highlighting, let's highlight this in green. If the degree of the numerator is equal to the degree of the denominator. So these are equal. You look at the coefficients. So you're looking at the coefficients of your highest terms, and that is what the horizontal asymptote is. So going back to our example 3. So I'm ignoring everything except for the leading term. So I have y equals 2x over x. So I'm ignoring everything else. I'm just taking the first term of both of those. X over x, those cancel, and so you're left with 2. So your horizontal asymptote is at y equals 2. And so that is this line here, I'm really bad at drawing straight lines. It's supposed to be a horizontal line, but that's where that is. It's at y equals 2 instead of y equals 0. And so you just ignore everything except your first terms, the x's cancel, and all you're left with are the coefficients. You ignore the plus 1. You just ignore everything else. You're only looking at those first terms. I usually go, so you'll learn more about this if you go to pre-calculus and go to calculus. There's this thing called a limit, and it's as things go to infinity. So if you pretend you put in a giant number in for x, you would have on the top 2 times a giant number plus 1. 2 times a giant number is giant. 2 times a giant number plus 1 is still giant. So that plus 1 doesn't really matter. And that's why we ignore it when we're looking at the horizontal asymptote. And it's the same thing in the bottom. If you plug in a giant number for x, subtracting 5 from a giant number is still giant. And so you can effectively ignore it when you're looking for asymptotes. And so that's basically what it means to find the limit, but that's something at the very end of pre-calc and for calculus. Okay, so next I'm going to find the intercepts. So I'm going to start with the x-intercept, and that is where for the x-intercepts we always take the numerator and set it equal to 0, because when you set your equation equal to 0, your denominator is always going to be multiplied by 0 to get 0. So the x-intercept comes from the top. So we have, if it would let me draw, 2x plus 1 equals 0. And so I'm going to solve that for x. So I'm going to first subtract 1 from both sides to get 2x equals negative 1. Then you're going to divide both sides by 2, which gives you x equals negative 1/2. And so that is where our x-intercept is. And you can barely see it on our graph. Uh-oh, Elsie lost audio. Those of you who are still on, can you hear me okay? Hector, David, are you guys able to hear my audio? Okay, so Hector can hear me, so I'm assuming that that is on Elsie's end. So I don't know how to fix that. Hopefully we'll come back for her. Okay, David, you can hear me okay. Okay, because I was having audio problems yesterday, a lot of audio problems. But if 2 out of 3 can hear me, it might be just temporarily in her end. Okay, so our x-intercept is at x equals negative 1/2, which you can barely see on the graph. But you can see that it's crossing the x-axis, and so it's probably around there. If you zoomed in, if we were on decimals, you can zoom in and see that. Now the y-intercept, that is where you set x equals 0, which we are allowed to do here because our vertical asymptote is not at 0. So we can plug x in, 0 in for x. So we're going to say y equals 2 times 0 plus 1 over 0 minus 5. So 2 times 0 is 0. So we have 1 on the top, and then 0 minus 5 is negative 5. So we have a y-intercept at negative 1/5, which also you can kind of see on the graph, but you'd have to zoom in a lot to see it. So we do have x and y-intercepts in this example, unlike the previous 2 that we had. Are there any questions about this example? Okay. Example 4. So here's one where we got something interesting going on between the 2 endpoints. And so I mentioned this, I don't think any of you were logged in at the time. But we have 2 basic shapes. And so, but what can happen in the middle of those shapes, there could be other things going on, but there's two basic shapes on the left and the right side, and these are the two basic shapes. So far we've been seeing both of those. So we had the first basic shape here, this was the second basic shape, this one's the third basic shape, but it's just sort of flipped or so. Now this is the second basic shape, but with something going on in the middle, something interesting. So I'm going to start with the domain and just fill that in. And I always start with the domain because I always forget to find the domain. So by making sure that I do that first, then I never forget. So this is all reals except blank. And then I will fill in that blank after I find the vertical asymptote. So vertical asymptote, that is where your denominator is equal to 0. So we have x squared minus 4 equal to 0. So now we're solving a quadratic equation. This is one that we can solve by taking square roots. So I can add 4 to both sides, which gives me x squared equals 4. Then I'm going to take the square root of both sides. And remember, when you take a square root, you get a plus or minus answer. So we get x equals plus and minus 2. What this means is that we have two vertical asymptotes. We have one at -2, which is right here, and you can see it's getting vertical there. And then we have one at +2, which again, at +2 you can see it's getting vertical. So we have two vertical asymptotes, which means there's two values excluded from the domain, 2 and -2. So we have all reals except for 2 and -2. Next is the horizontal asymptote. And so I'm looking at the degree of the numerator compared to the degree of the denominator. So we have a quadratic in the numerator, which is degree 2. We have a quadratic in the denominator, which is degree 2, so they're equal to each other. And so this is still case 2. And case 2 is when you ignore everything except for your first terms. So in this case, I'm just looking at the 2x squared and the x squared, and I'm ignoring everything else. When you follow the rules of exponents, those cancel, and once again our horizontal asymptote is at y equals 2. So that's here on the graph. So because we had a quadratic on the top and the bottom, that means it's case 2. Their degrees match. So you only look at the first terms and then cancel what you can to get your asymptote. Now let's find our intercepts. So the x-intercept. That's where the numerator is equal to 0. So I have 2x squared plus 1 equal to 0. So I'm going to solve that for x. So I'm going to start by subtracting 1 from both sides. And that gives me 2x squared equals -1. Then I divide both sides by 2. This gives me x squared equals -1/2. Okay, so Elsie, for the vertical, use the denominator. That is correct. And then for the horizontal, you only use the first part of both, and that is correct when the degrees are the same. So you have to look at what the degrees are. And for this case, because it's a quadratic on the top and the bottom, you only use the first part of both. Great. I'm glad your sound's back. That's awesome. So going back to this x-intercept I'm solving for, I'm going to take the square root of both sides, and I'm taking the square root of negative, which means I'm going to get an imaginary number. And an imaginary number means there's no x-intercept. So we're going to get plus or minus I times the square root of 1/2. And so that means there's no x-intercept. And you can see that on the graph, that it doesn't cross. You can't see it cross the x-axis at all. Next is the y-intercept, and that's where you plug x equals 0. So I'm going to have y equals 2 times 0 squared plus 1 over 0 squared minus 4. So 0 squared is 0, and 2 times 0 is 0, so I'm left with the 1 on the top and negative 4 in the bottom because 0 squared is 0. So our y-intercept is at negative 1/4. So we have no x-intercept, but we do have a y-intercept. Are there questions? Okay, so now moving on. Example 5, this is when we're going to have a slant asymptote, because you can see that there's no horizontal line that it looks like. It looks like there's a slanted line there that it's sort of following. So that's the slant or oblique asymptote, where you have to do long division or synthetic division. So we're going to go through all of our steps, starting with the domain. So all reals except blank. Vertical asymptote. That is where the denominator is equal to 0. The denominator is x minus 2, so I have x minus 2 equal to 0. You solve for x, you get x equals 2. So that is here. So our domain is all reals except x equals 2. Now, our degree of the top n of x is 2, and the degree of the denominator is 1, because it's linear. So the degree of the top is greater than the bottom, and this means we need to do long division, or we can do synthetic division. So here we can do synthetic division because we're dividing by x minus a number. So we are going to do synthetic division. So I'm going to set this up so I have a 1 for my x squared, a 2 for my x, and then a minus 4. And for the value of the synthetic division, you use the vertical asymptote, which is at 2. And so now I'm going to do my synthetic division. So first I do 2 times 1, which is 2. I put that on top. Then I add 2 plus 2 is 4. Then I take 2 times 4, which is 8. 8 minus 4 is 4. So now our asymptote here comes from everything but the remainder. You ignore the remainder to find your asymptote, and this is the slant asymptote. And this is going to be y equals mx plus b. So we're going to get y, oops, not highlighter. So we're going to get y equals 1x plus 4. So it's because it's a line, it's mx plus b format. So if you had y equals 1x plus 4 and you graphed it, it would follow this slanted line here. So it's called a slant asymptote or oblique asymptote. I'm going to just skip the x and y intercepts because I don't have any room on here. But you can see on the graph that there is both an x and y intercept because you can see that they cross. There's two x intercepts because the numerator is x squared, and then there is one y intercept. Are there questions on what I've done on this slide? Okay, so now example 6. So you can see that we have another slanted asymptote here, and then this has some interesting things going on in the middle. The middle looks like a cubic, and you can see that the numerator looks like a cubic, so those are sort of related. So we're going to go through everything. We're going to do the domain. All reals except blank. Vertical asymptote. That's where the denominator is equal to 0. So our denominator here is x squared minus 9. And I can solve this by taking square roots. So I'm going to first start by adding 9 to both sides, which gives me x squared equals 9. And then I'm going to take the square root, and the square root of x squared is x, and I get a plus or minus 3. So we have two vertical asymptotes, and they are at 3 and negative 3. So those are the values not in the domain. So I'm going to just draw those in. Those are roughly where those would be. Now we have a slant asymptote, and so that's where we need to do, in this case we have to do long division because our denominator is not linear, it's quadratic. So we have to do long division. So this is just the degree of the numerator is 3, and that is greater than the degree of the denominator, which is 2. So because the top has a bigger degree than the bottom, we have to do long division in this case because we're dividing by quadratic. So I'm going to set up my long division. I have x cubed minus 3x plus 5. And I'm going to divide by x squared minus 9. So if I just look at the first terms here, we haven't really long division in a while. We're just looking at our first terms. So an x squared times x will get me x cubed. So I have an x cubed underneath. And I also multiply negative 9 times x, which is minus 9x. I draw my line, I'm changing my signs, and then I combine. X cubed minus x cubed is 0, minus 3x plus 9x is 6x, and then I drop down my plus 5. Now, x squared times what gets me 6x? That's nothing. I can't multiply x squared by something to get 6x. I'd have to divide it. So that is a remainder. And so for our slant asymptote, we just care about what is on the top. So this asymptote is going to be just y equals x. And so that's what this line is following. You can see it goes through the origin. So it's just y equals x is our slant asymptote. And it looks like, let's see, the graph definitely has an x-intercept and it may or may not have a y-intercept based off of how close that graph gets to 0. It's hard to tell. So are there questions about this slide? Okay, so now this is my last slide, and this is something special. I have this rational function here, but when you graph it, all you get is a line. And you may be wondering, how the heck does that happen? So what happens here is that the numerator here factors. So if I factored the top, that's x minus 5, x plus 2. And then I have x plus 2 in the denominator. So if you factor it, you can see that the x plus 2's cancel. So those would cancel out and you're left with x minus 5. Now remember, way back in week 1, we had to give the domain. We had to say that means x cannot equal negative 2, and that comes from the x2 we canceled. So your graph, your function, is y equals x minus 5, but x can't be negative 2. The domain is all reals except x equals 2. That's what's canceled. X equals negative 2. So that's what's canceled out. And so it looks like a line. You can't really see it here, but at x equals negative 2, there should be an open circle or a hole, because that is not in the domain. It was canceled out. So your graph looks like a line except for that one spot where you have an open circle because there's a hole. So there's no asymptotes at all. They don't exist because when you simplify it, you get a line. But there is a hole in our graph. And so this is a special type of rational function that simplifies to a linear function. And you have to be careful because Desmos does not put a hole there. If you graph that on Desmos, it doesn't put an open circle, but if you clicked that area, it would tell you that it's a hole. It tells you undefined. So it's sort of misleading if you graph it on Desmos because they don't specifically mark that hole. So are there questions on this example, example 7? Okay, so that was all the examples that I had. You may want to watch this a second time once I post it, just to verify that you understand it, but basically you're doing the same things over and over again. The hardest part is just understanding the horizontal, whether it's going to be case 1, case 2, or case 3. But most people do really well in the homework this week because I guess because you're doing the same thing over and over again, so it's usually not too bad. And it looks like Blackboard is back up. Okay, I don't know if you guys noticed. I noticed before I logged in here. I was trying to get on the Blackboard. Blackboard was down. It looks like it was down for about an hour, but now it's back up. So if you guys wanted to go back in and do your work now, you can. So any last minute questions before I end this and then start like getting it uploaded and all that stuff? All right. Hopefully this was helpful. It didn't confuse you more. But of course, you know, you can always ask me questions. So I get to do another one at 7 for pre-calculus. So if you guys are going on to pre-calculus, you will still get live sessions, so you can look forward to that. They are learning about trigonometry this week, so that's going to be fun. Sine, cosine, all those fun things. So I'm going to pop off so I can get, refill my water and everything before I do that at 7. Hopefully I will talk to you guys again. This is the only live session I had scheduled because this is basically the whole everything you needed to know for the week. So I hopefully will see you guys next week on Wednesday for the introduction to week 7. So, all right, you guys have a fun night, and hopefully